speaker is Pablo Martinez, and he's going to be speaking about automated distribution of quantum circuits via hypergraph partitioning.
Hi, thank you. Well, first of all, I'm going to try and motivate why we want to have distributed quantum computing. And to do so, I'm going to talk about a particular technology that it's very, where distributed quantum architectures are very natural. And this is the trapped ion quantum computer. So basically, the idea of a trapped ion quantum computer is that you have a device, which is the trap, which contains some ions, which are confined there, and you try them to be as stable as possible. And then you, that's your memory, so to speak. And then you shine lasers onto that in order to do computations and change the state. And you need to be able to do universal computations on that. And there's a trade-off between the amount of qubits you have in your trap, so to speak, the memory you have, the amount of memory you have, and how stable these qubits are, because basically the more crowded your trap is, the more crosstalk you have between the ions. And basically your ions are the thing that are storing the qubits. Some state of the ion represents the qubit. So we may regard a trap as a quantum processing unit, an autonomous one. It can do universal computation. But then if you want to have more qubits than what your trap has, you might want to have multiple traps and then have some communication between them. And the problem is that this communication is going to be very, very costly. So of course, what you would like is to reduce as much as possible this amount of communications. Okay. So from the perspective of programming and compilers, what I am doing in this project is I assume you write some program in some language, could be Cooper, could be Q#, whatever, and you have your compiler for that program that is going to output a circuit. And what I am doing is this distributed part, which takes a circuit and having some information of the number of QPUs you have, the number of traps you have, and the size of them, the amount of qubits they can manage, you obtain a distributed circuit on that architecture. So, of course, if you want to do some operation that involves qubits in two different QPUs, you need them to be able to coordinate in some way, to share quantum information. The standard way of doing so is through quantum teleportation, which basically allows you to send a quantum bit of information by consuming something that we call an E-bit, which is, for example, a belt state is an E-bit. It's a maximum entangled quantum state. So you have a pair of qubits that are in a particular state. One QPU has one of the qubits, the other QPU has the other qubit, and they can talk through that. They can send one qubit of information through that. E-bits are very expensive to produce, and of course, as I said, this is the resource that you want to minimize when distributing a circuit. So how do we implement non-local gates using E-bits? By a non-local gate, I mean a 2-qubit gate, for example, that it's applied on the qubits of two different QPUs. So for example, here, what I will be considering, the 2-qubit gate that I will be considering is the control set, which is very similar to the control node. The main interest here is that both of its inputs are symmetric, so we don't have to care about the two different roles that in the C node the two different inputs have. And here, in the left, what I have is a circuit that I intend to distribute into two different QPUs. The bottom QPU and the top QPU. And this dashed line is the boundary between them. And right now it's cutting these control sets. And therefore, I can't implement them, at least not directly, because this would be non-local. So what I want to do is to have a black box. For example, this is the first option. Have a black box that sends my qubit in the QPU A to QPU B. QPU B locally now does the control sets and then sends back the qubit. There's a better option. In this option, you require 2 EBITs, one for each box. There's another option which uses only 1 EBIT, but it has a caveat. It has a slight problem that I will consider in the next slide. But for now, what you use is you use 1 EBIT, just one. So the boxes here don't have an EBIT inside them. And what you're doing is you untangle. And basically, after the entanglement, you have that the qubit that is held here is entangled with this one. And whenever this one is 0, this one is 0. And whenever this one is 1, that one is 1. They are entangled. Now you can apply control. You can apply control operations on the QPU B using that information. And at the end, you want to disentangle. So you go back to the original situation. So in these boxes, what you have is these things here. You will recognize that this is kind of half of a quantum teleportation, where you are only doing one of the 2 measurements. And then at the end, you do the measurement to complete the teleportation, but actually you do it in the other qubit. So basically, you are destroying the qubit here and recovering the information on the original one. And as I said, there's a caveat. And the problem here is that if you do this option, I say there's a one-way communication only. You cannot change the state here by applying an operation. You can only use it here as controls of as the control of controlled operations in your in your remote QPU. If you do, it's just they are not equivalent. In the case of teleportations, you could do this, but then again, you would be using one teleportation here. You could do this and then teleport back. So there's a trade-off here. So this approach has been known previously, and this approach is the one I'm using for the most part. And by the end, if I have time, I will explain a little bit of how I also include teleportation here. OK, so notice that we could implement 3 or more, as many as we want, control sets using a single EBIT with the second option. We call this control set Z-set grouping, and it is possible as long as all control sets are acting on the same qubit, which is the one that we're sending, and there's no gate on the qubit in between control sets, as I showed in the previous slide. For our purposes, we'll assume, without loss of generality, that all our circuits are built from 1 qubit gates and control sets exclusively. This is a universal gate set, so there's no problem. There's algorithms to go from any gate set to this gate set efficiently. So now, stating the problem more clearly, what we want is that given a quantum circuit and a number k of QPUs that are all available to you, you want to split the circuit into fragments so that each fragment is run in one of the QPUs, and you are using the minimum amount of EBITs possible. So there's previous work on this. For example, in this paper here, they did this study for one particular algorithm, for the Shor algorithm. They took the circuit of the Shor algorithm and explored one way of partitioning it. On a later work, they tried to automatize that, so you don't have to take a circuit and by hand find the better way of partitioning it. Quite obvious solution is to use graph partitioning, because they're basically the same problem. So what you do is, for each qubit and each wire that you have in your circuit, you consider that you have a vertex of a graph. And for each Z-set, you consider you have an edge, because there's communication between those 2 wires. And then your problem is simply obtaining a graph partition that has the least amount of cuts possible. The partition tells you how you are assigning qubits to the QPU, and the number of cuts is related to the number of EBITs you will use. And there's a problem here. The problem is that, as I explained, one of the the thing that makes this problem non-trivial is that you have these control set groupings that allow you to implement more than one non-local gate using a single EBIT. And in this case, in this naive case of graph partitioning, the graph partitioner doesn't know about these groupings. So if you want to optimize for that, you have to optimize for that at a later stage, which requires, for example, some, in this paper, right? In this paper, they use some exhaustive search, and it requires, the problem is that your optimizer is not taking into, the graph partitioner is not optimizing for that at the start. So the algorithm we are using is, instead of considering graphs in this way, where you are cutting 3 edges, but you actually only require 1 EBIT, we include 1 vertex per C node, which is going to tell you when the partitioner assigns it to a QPU, it's going to tell where is it going to be actually executed. And in this case, if you have, instead of having 3 edges between alpha to D, beta to D, and gamma to D, given that all of them can be grouped, you have a single hyperedge. And therefore, if your partitioner finds a partition that only cuts, in this case, 1 hyperedge, you know that it's going to be possible to implement it using a single EBIT. And this is now the hypergraph partitioner is aware of control set groupings. So, oh, I don't know why this is, OK. So here's an example with a simple circuit. What we're going to do is go wire by wire, looking at the connections, and building the hypergraph. And it should be fairly straightforward. Here, for example, these two can be grouped together. So we have a hyperedge instead of a standard edge. Again, it happens the same. And we finish our hypergraph. This is the complexity of this is just 2 times the number of control sets you have. So this part is perfectly scalable. Now, the difficult part and the time-consuming part is to actually run the hypergraph partitioner. But there are third-party software for that are developed by experts on the field, so you can trust that they've done as good as they could do. And we are taking advantage of that. And it's going to give you some partition. For example, it gives you this one, which is telling you that you should cut these 2 hyperedges. And now you can very easily come back and write your circuit. So you start from left to right. These ones tell you that this hyperedge is cut, and you need to use 1 EBIT. So you use CZ grouping, and you implement these 2 using only 1 entangler and 1 disentangler. So it's only 1 EBIT used. Gamma, for example, here, none of the 2 edges are cut, and therefore it means that it's locally implemented, and you don't need any EBITs here. And for the last 2, you do the same as before. And therefore, this is your circuit. So we proved, and it was a simple proof by induction, that in fact, when you build a hypergraph and you get a partition, if your partition only cuts n hyperedges, you will be able, by this procedure, you will be able to create a circuit a distributed circuit that only uses n EBITs. And this is something that I wanted to talk about. That is this thing that you will have a very, very large circuit probably. And the connectivity is going to change over time. So, and this is a problem because then your hypergraph is not going to have useful information about the connectivity. The partition is not going to be able to optimize for the particular connectivity of different stages of the circuit. So what you want to do is split the circuit into different stages and then find the optimal partition for that stage and then glue them together through qubit teleportation. And this is what we did. And then the evaluation, well, this is implemented in Cooper, and the main reason was so that we had these very big circuits to test and to benchmark our algorithm on. And we did. And this graph shows you for these 5 problems the amount of EBITs you required with respect to the total number of control sets you have in the circuit. And this bar here, this dashed bar here, tells you the amount saved by using this hypergraph partitioner instead of the graph partitioner, and therefore using CZ grouping instead of doing the naive solution. So that's all I wanted to talk about. This is the availability here. You have the code in here, and the paper, you can find it in the archive. And there's some future work that we would like to work on. Thank you very much.
Any questions?
So I just didn't quite catch what you were comparing to in the final charts.
Right.
So you saved EBITs compared to what?
So in this chart what you're showing is the y coordinate here tells you the proportion of EBITs versus the total amount of control sets. Because you could think that if all of your gates were non-local, then you would require, and if you require 1 EBIT per gate, this proportion would be 1. So in principle, the important part here is that if you use naive graph partitioning where you are not considering C-set groupings, the proportion that you get for these circuits is this one. And if you are making use of C-set grouping, you gain some additional, so these EBITs, you no longer need them. So for example, in cases such as ground state estimation, you remove half of the EBITs that you require. And in other cases, of course, the gain is not that big, as you would expect.
And your theorem says that this is optimal, right?
Well, it doesn't say it's optimal. It says that if your graph partitioner, if your hypergraph partitioner finds a optimal solution, then it is an optimal solution for the quantum distribution problem. But of course, your hypergraph partitioner, you can't expect it to find the optimal solution because it's an NP-complete problem. So it depends on how good the hypergraph partitioner is.
So you started off by saying that this is sort of specific to ion trap machines. Can you say something about, like, is there a reason? Are ion trap machines special in a way that there's sort of a limit to how many you can have on a local machine, and it's easy to do this kind of communication between them so that it makes sense and it doesn't make sense for superconducting qubit machines?
Well, it does make sense for superconducting machines, and there's some experimentalists that have proposed distributed architectures for superconducting machines. It's more about the advantage that ion trap has. The problem is that doing these quantum channels where you need to do measurements and do classical corrections with your measurements, it takes a lot of time. And therefore, you need qubits that have a long coherent time. And the advantage of ion trap quantum computing is that it has the longest coherence time in its memory. And therefore, that's why it's the most natural architecture to use. But it's not limited to that. And of course, this algorithm is completely ignorant of which architecture you're using.
Thank you very much.
Thank you.
Okay, so we have one more talk. Robert is going to set that up. This was a talk